Here's problem number 42 from section 3.1. We've got a lot of subparts here, so let's go through them one by one. In part A, it asks to find f prime for the values for the function when x is less than 1. So this will be the limit as h approaches 0 of f of x plus h minus f of x all over h. Now in this case, because x is always less than 1, we'll be using that first definition in our piecewise, and that is going to be x plus h squared, and f of x is x squared over h. The limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared all over h. These x squareds cancel. There is a common h in the numerator, which I can factor out. These h's cancel. When I apply the limit, I get 2x. In part B, I do the same thing, except I'm now bigger than 1. So I still have the limit as h approaches 0 of f of x plus h minus f of x all over h, and that limit as h approaches 0 is now of 2x plus h minus 2x over h, where the limit as h approaches 0 of 2x plus 2h minus 2x over h. 2x's cancel, these h's cancel, leaving me with a 2. Now, part C. In part C, it's asking what is the limit as x approaches 1 from the negative side of f prime of x. Well, we've already found out what the value of f prime of x is while we're less than 1. So really this becomes the question, what is the limit as x approaches 1 from the negative side of 2x? And that value is 2. Part D. The limit as x approaches 1 from the positive side of f prime of x. Well, we've already found what that value, the value of the f prime function is when we're above 1. That's equal to 2. Part E. Does the limit as x approaches 1 from the positive side of f prime of x equal the limit as x approaches from the negative side of f prime of x? And the answer is yeah, they both equal to 2. That is a true statement. The right-hand limit and the left-hand limit agree. Part F. Now, here's what they're trying to get you to understand. This, while it is true, is not sufficient to get all the way to h to say that the limit that f prime of 1 exists. And the reason being is that in part F we can do a left-handed derivative. The limit as h approaches 0 from the minus sign of f of x plus h minus f of x all over h. Now, in this case, we know x is 1. So let's go ahead and let's change our x's to 1s. And a little note here, f of 1, as defined by a piecewise function, is equal to 1 using the x squared. So now we have the limit as h approaches 0 from the negative side of f of 1 plus h. H is a little bit negative, so we're a little bit below 1, so that's going to be 1 plus h squared minus 1 over h, which is equal to the limit as h approaches 0 from the negative side of 1 plus 2h plus h squared minus 1 over 1. The 1's cancel. I can factor out an h out of the numerator, these h's cancel, and I end up getting 2. Well, what about in part G? What happens if we do the right-hand derivative? The limit as h approaches 0 from the positive side of f of 1 plus h minus f of 1 all over h. The limit as h approaches 0 from the positive side. Now, this is f of 1 with h being just a little bit of positive. That means we're using the 2x definition now. So that's going to be 2 times 1 plus h minus f of 1, which is 1, over h, which is equal to the limit as h approaches 0 from the positive side of 2 plus 2h minus 1 over h. And you'll see that in this particular instance, we do not get that nice cancellation that we have. In fact, if we were to graph this, as h goes to 0, this thing goes way up and ends up equaling infinity, or the derivative, that limit does not exist. Now, because the left-hand derivative and the right-hand derivative don't agree, we say that in part h, f prime of 1 does not exist, because the left-hand derivative does not equal to the right-hand derivative. Now, you may say, but wait, we looked over here and they matched. What went on here? Well, what went on here is the fact that there's a discontinuity in this function, and because of this particular derivative approaching infinity, that happens because of that discontinuity.